Welcome back to this tutorial series on composing with OpenMusic, and specifically in this series we're looking at constructing an interval class calculator. So if you haven't seen the previous video, you'll probably be a little bit confused if you haven't looked at that before. So I'd encourage you to check that out. We're going to be picking up where that video tutorial left off. So let's open back up the patch we were working on last time. And last time we were able to successfully make this OM loop object that would run through this chord and check each of these intervals and return the size of the interval in terms of MIDI cents, which is really great, really useful to do. But now we want to kind of move on to the next step, which is going to be converting these MIDI cents into into pitch classes. So what's the difference between the MIDI cents that we're working with and the pitch classes? So if you're already familiar with kind of the background behind working with pitch classes, that this may be a little bit redundant. But for those of you who aren't as familiar, I'll just give a quick explanation. So when we're working with pitch classes, this is a way of generalizing the pitches that we use, for example, on a piano. So what I mean by generalizing is it's a way of saying, for example, any two, let's just say like F sharps. So any two F sharps, we know that these notes are produced by different frequencies. And again, in OpenMusic, they're represented by different MIDI cent values. But we still call them both F sharp. And so when we're working with pitch classes are a way of generalizing away from a difference in octaves. So it follows a principle that we call octave equivalence. And what that means is simply we're going to treat any F sharp as being the same as any other F sharp, no matter how high or how low in pitch it is. And because we work with 12 chromatic pitches in most Western classical or art music traditions, we end up with 12 pitch classes, and we typically start with C, and we cycle through all the chromatic pitch classes here: F sharp, G, G sharp, A sharp, B, and of course we're also including enharmonic equivalence. So you could replace A sharp with B flat, and we mean the same thing. But so what we do is we assign just a number to each one of these. So C is 1, or C is 0, C sharp is 1, D is 2, D sharp is 3, E is 4, F is 5, F sharp is 6, G is 7, G sharp 8, 9, 10, and sometimes we'll represent that with like a T and an E for 10 and 11. For now, we'll just go with this, 10 and 11. Okay, so what this means is we can represent any sequence of pitches, regardless of how high or low, in the tessitura we're working with, by using these pitch class integers. And that's what we're going to want to do here, because our interval classes that we'll be working with later to do some analysis depends on this concept of pitch classes. Okay, so with that little bit of background, we can go over here and take a look at this next component that we'll be using. So this is a patch that I made. It's a really simple one. And basically what it's doing is it's taking the output of a chord sequence and converting the MIDI cent pitch values two pitch classes. And so the first thing that we're going to have to do is divide by 100. And the reason we're going to do that when taking the output of, for example, this loop that determines the interval distance between chord tones is because we want to get rid of the extra kind of information that those MIDI-sent representations are holding. So because we're not working with microtonal music at this point, it's actually unhelpful to have kind of that extra stuff. Let me just select one note. Have the extra zeros after that. So we're going to divide by 100, and we'll just end up with these numbers. And so that's super helpful. Now, we could end up with a little bit of a problem, for example, say if we increase that interval, and we'll see after dividing the results by 100, we end up with a 20. And a 20 is outside of the bounds of our pitch class space that we've set up, where B as 11 is about the highest we can go. So what we're going to do is we're going to use modular arithmetic. Sometimes it's referred to as like clock arithmetic, especially if you're working with a group of 12 objects like we are here. So you can think of this as different positions on a clock, where maybe C would be at 12 o'clock, and this F sharp would be at 6 o'clock. Is that right? No, I guess it would be, yeah, that's right. Yeah, all the way across the circle of fifths. And so to make OpenMusic do this, we're going to use this object. Now, one thing that I should point out is this is from a special library, I believe. Let me just double check on that real quick. This object I'm using, I think, is from the OM Tristan library. OM Modulo. Let's see. Yes. Okay. So if you want to use this object for calculating modular arithmetic, you will want to download the OM Tristan library, and this is a library, I believe, that was put together by Rosaline Heers. I don't know how to pronounce her name, but she wrote a dissertation which is available as a published book from IRCAM about the music of Tristan Murail, the spectralist composer who has worked with OpenMusic extensively in composing his works. So if you're interested in using this, and again, I really would recommend that you get this library package. It has a lot of useful objects. What you'll want to do is pop over to your browser. You should be able to just type in something like OM Tristan library GitHub. And GitHub is where a lot of these library packages are stored. I apologize, my connection's a little slow today. Yeah, here we go. And if you want a list of available OpenMusic libraries, this link is a really great one, where it has sort of centralized the most frequently used OpenMusic libraries. But you can go ahead and go to GitHub, and you can find this library package there. You'll want to download it, and then you're going to have to drag it into your OpenMusic directory. And so there should be, like a README, and that would give you some information on exactly how to install it. But I'll just show you really briefly. Basically what this looks like is navigating to your root directory. So here's mine, and a folder for OpenMusic. And then the libraries folder here will have libraries. And again, there are There are dozens of libraries that you can download and use. Let me see if I can find, oh, I'm Tristan in here. Here we go. Here we go. And sometimes if you download from GitHub, just be aware that it might have, when you extract this package, it might look like this, with a little appended -master, and you'll probably have to rename that and get rid of that for OpenMusic to identify the library in its libraries folder. So once you've dragged it into there, you can go back to OpenMusic, and what you'll need to do at this point is tell OpenMusic to load the library on startup. So you can do that by going to Preferences, and then clicking this Libraries tab, and then you're going to need to scroll through and find the library that you want to use, and you're going to have to select it. So yeah, here we go. Oh, I'm Tristan. You'll have that selected. You'll hit Apply, OK, and at that point you should be able to type in om.modulo and have this object appear. So we're going to use this this modulo object. And so this is the inlet that will take the data that we want to process. And then as you can see, we're going to use modulo 12 arithmetic. So now that 20 that we have at the end of this list should be wrapped around, yeah, there we go, wrapped around to 8, which is what we had before, you'll remember. That was the same that we had before. So all that's doing is getting rid of the distinction between pitches that are the same pitch in different octaves, right? So that's basically what that is accomplishing. And now I have a flat object here, and I'm not entirely sure why. My guess might be if it was working with different layers of nested lists, but I'll go ahead and include that again. And so now what I'm going to do is I'm going to select all of these, and I'm going to make a new patch, and we'll call this chord sequence to pitch class. And here we've got the window, and sometimes this happens where it gets all spaced out, but we'll just quick tidy this up. Move it up here, add an inlet and an outlet, and connect those up. And now we'll have a patch that will change the MIDI sent information coming out of this chord sequence object to representing pitch classes, which will help a lot. And in this case, as we'll notice, because we've already processed the information to be representing intervals, the distance between any two chord tones. Really what we're getting at now is interval classes. And we're almost at interval classes. We're not quite there yet, and I'll explain why here. So the last step that we'll need to do is make another loop object that's going to go through the results that we get from converting these MIDI sent intervals to these kind of modulo 12 interval classes. And so the reason why we still have one more step to go, let me make another chord sequence and I can demonstrate, is it really doesn't make sense to have these last two numbers here when we're thinking about types of intervals. So let me explain what I mean by that. We really only have 6 types of intervals, and again, I apologize if this is something that's really familiar to you. But so we can have a minor second, and we call that an interval class 1, as in 1 semitone difference. So this would be a major second, and we call that interval class 2, a minor third, and really that should be an E flat, but we'll forgive OpenMusic for now. And that's going to be our interval class 3, interval class 4, interval class 5. And then once we get to the tritone, going from C to F sharp or G flat, that's the last interval class we can use. And the reason for that is because now we have divided our chromatic pitch space in half. So if we have 12 chromatic pitches and we have an interval of 6 semitones, we've kind of wrapped, halfway from 12 o'clock to 6 o'clock on our circle. So any increasingly larger intervals will already be repetitions of what we had before. So before we had interval class 6, the tritone, we had a perfect fourth, which was interval class 5. And that's also the first interval class we'll get on the other side of the tritone, perfect fifth. Then we get a minor sixth, which is the inversion of a major third. Then we get a major sixth, which is the inversion of a minor third. We get a minor 7, which is an inversion of a major second. And then we get a major seventh, which is going to be the inversion of our minor second. So if we cycle through chromatic pitches, we get interval class 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1, and then back to the unison. So 6 is really the upper limit of what we can have in terms of intervals. And that's why this 7 and this 8 don't make sense. Really what this 7 is an interval class 5. And then this 8 is going to be an interval class 4. So what we want to do is make one more loop that will process the data that we have arrived at and wrap it around again. So what we're going to do is we're going to make a new loop object here. We're going to add an inlet with Control-Shift greater than. And then inside this loop, we'll work off this messy template I have from some past patches. So we're going to do kind of the same process we did in a previous loop, except now that I'm looking at this, we can really clean this up. So yeah, we're gonna clean this up. And yeah, oh totally. Okay, so what we're gonna do, instead of using a for loop like I have in my default version of this patch, we're going to use list loop, which just automatically cycles through the elements of this list. So I can replace these 1, 2, 3, 4 objects just with a list loop and not lose anything. Okay, so what we want to do now is come up with a test to determine if the information that we got from the previous step is good or bad, right? So these first 4 values are all within the bounds of our interval classes, but these last 2 aren't. So we're going to make OM greater than, and we want to test if the value that we're seeing at any given point in this loop is greater than 6. Because if it is, we're going to need to change it. If it's not, we can just leave it. So that's where our OM if object comes back in. I'm going to select that, Control-Shift greater than, and add that little else inlet. So we're going to test to see if the value is greater than 6. And if it is, we're going to subtract that value from 12. And you'll notice I have a patch here to do that, and this really isn't necessary. This is just sloppy. All it's doing is subtracting from 12, and we don't need that to be its own whole little patch. I don't really know why I did it that way. So what we'll do is we're going to take the value, we're going to make an OM, oops, I got a pinwheel, OM minus. We'll make the first inlet argument 12, and then we'll take whatever value of our list is current at the moment. So 12 minus that value will be the result if that value was originally greater than 6. Otherwise, we can just let that value pass through our loop. And that's why that's going to route down to that else option. So now we've got that all set up, we can do the last steps, and I'm going to move these over just a little bit, make it a bit more compact. We'll collect these values, and remember we want this to be iterating each time and then collecting the results and delivering a final result. So we'll tidy this all up, move that over, and now we've got our nice little loop. And now let's check and see if the 7 and 8 really do get reassigned to the values that we would expect. And sure enough, they do. 5 and 4. Awesome. So now we have, I think, pretty much wrapped up this this process here. So let me just double check the last little details. What we would want to do now would be to kind of streamline this patch here. And so what we're going to do, we're going to bump this over, connect this to an outlet, and we can get rid of this this one. That was just for the purposes of demonstration. So we can plug that down there, move this here, tidy up this patch. I'm just going to resize that, save that and close. And now as I evaluate, sure enough, I get the values that I would be expecting. So let's just see. Wait a second, is this right? I know what's the problem. When I set up this example, I was using the wrong interval at the end. So let's change this C# down to a B. There we go. And so now our little patch here to detect the interval list is working just like we would expect. And sure enough, this chord has all the intervals that we could expect to find in 12-tone equal tempered music, which is really great. So you may be wondering what the point of something like this is. And in an earlier video, I just quick demonstrated ways that I have used this in the past. So I, in some of my composition practices, I will, let me find the right one that I want. Is this it? I will use a patch like this that will determine the interval classes to analyze some sonorities that I want to use in my pieces. So for example, this collection of pitches I pulled from a favorite work by Maurice Ravel. And then I have this patch that will go through and determine the normal form of the set as well as the interval class vector. If you're interested in that, I'll post a link to a description of the interval class vector. But it's basically just a list of how many intervals of each type appear in this collection of pitches. And then I've also been able to use this patch in conjunction with kind of these larger groups of patches to select chords that have maybe specific interval class content. So for example, here would be a list of some chords. This one has at least one instance of every interval. Other ones are grouped specifically by pairs of intervals. So here you can see some examples of those. But for me, this has been something really, really useful in my composing. It's been a lot of fun. And again, if you're interested more in learning about kind of the rationale behind composing with interval classes, I'd encourage you to look a little bit at some of the ideas of Witold Lutosławski. There's a really excellent biography of Lutosławski by Stephen Stuckey, where he looks at some of these techniques in Lutosławski's music. So we have successfully built this interval class calculator, and I hope that this was useful. I'm looking forward to pushing ahead with some other examples of some useful patches that I've been able to utilize over the past year or so. And again, if you have any questions or comments, or if you're looking for some further resources, leave a comment, and look forward to seeing you in the next video.